The next topic in additional mathematics is surds. Okay, so a radical is any number which is with the radical sign, meaning the number must be under the radical sign. A surd is a real irrational radical. So surds are present in solution to some quadratic equations. So it could be root 3. So the next point states that every surd is a radical, but every radical is not a surd. I'll explain right away. So for example, root 9 is not a surd because it can be simplified to 3. It must be irrational, meaning it cannot be written in the form p by q, where p and q are integers and q is not equal to 0. It cannot be represented by that, but then 3 can be. It's basically 3 by 1 or 6 by 2. So therefore, it's not a surd. It must be rational. And the next point is that it has to be a real radical, meaning you cannot have square root of -1. That would be not real because we still don't know the value of square root of -1. And the next point is that square root of a is a non-negative number such that square root of a into square root of a, meaning square root of a whole squared, it's equal to a. So that's the whole thing. Just remember that this is very important. Every surd is a radical, but every radical is not a surd. So radical can be irrational or rational, but a surd has to be an irrational radical. Okay, now let's do some properties of surds. So square root of a is greater than or equal to 0, and hence it cannot be negative. As we clearly know, square root of something has to be positive. And square root of a is only real if a is greater than or equal to 0. If it's a negative number, it would be an imaginary number. Yes, so it has to be greater than or equal to 0. And square root of a into b equals square root of a into square root of b. This is the property where a is greater than or equal to 0 and so is b. It must be greater than or equal to 0. And the next thing is that square root of a plus square root of b is not equal to square root of a plus b. So for instance, I'll just give an example. We'll take square root of, let a be 2 and b be 4. So square root of 2 plus square root of 4, I'll just tell you the answer. Square root of 2 plus square root of 4, that is 3.41, and square root of 6 is 2.44, meaning they're not equal. So therefore this property states that square root of a plus square root of b is not equal to square root of a plus b. And the next property states that square root of a divided by b equals square root of a divided by square root of b, where a is greater than or equal to 0 and b is greater than 0. So here it must be greater than 0 and not be greater than or equal to 0, because square root of 0 would be 0 and something divided by 0 is infinity, or in other words is undefined. So yeah, so b must be greater than 0. Yeah, so now I have solved a few examples here. So square root of 15 into square root of 4, we know this one, it's this property. And now we can multiply these two, meaning it's square root of 15 into 4, that is square root of 60. We can simplify this further, but we'll just leave it like that. And then we'll solve this also. Square root of 36 divided by square root of 7. So square root of, so this would be square root of 36 divided by square root of 17. It's because of this property, so that would be 6 divided by square root of 17. So you could remember all the squares, the numbers and its squares, like 1 is 1, 2 is 4, 3 is 9, If you really want to save time, like maybe a few seconds, then you could do it. Or I mean, you always have a calculator, right? So it doesn't really matter. But then if there are like no calculator questions, you might find it a little difficult because you'll have to like manually multiply it. Like if just say square 21 or something, then it might be a little difficult. It may be time consuming. So if you want, you could remember it, or else it's fine. So now you will have to solve these. I'll just solve maybe one of them. I'll solve this one. No, actually, I'll solve the third one. So the question states that square root of 21, you could also write this, square root of 12 into square root of 21 divided by square root of 4. We know that square root of 4 is 2 because 2 squared equals 4. So that would be square root of 12 into 21 divided by 2. So I've used one of the properties, and 12 into 21 is 252 divided by 2. We could simplify this. You can just use a calculator, and we get 6 root 7 divided by 2. So basically how we got this is we could write this into 36 into 7. We could split this down. We could write 257 as this. And then we know the properties. One of the properties is square root of 36 into square root of 7. This equals this. And we know that square root of 36 is 6 into square root of 7. So this, we have used one of the properties. Yeah. And we could cancel this out, meaning 3 root 7. So this would be our final answer. Yeah, or we could just leave it like this. I mean, either way is fine. But so that would be square root of 9 into square root of 7. So that would be square root of 9 into 7. That's square root of 63. These two are equivalent. This one equals this. Either way is fine. Each of the answers is fine. And the rest of the answers would be easy. Square root of 11 into square root of 11, that's 11 itself. And you just have to multiply these two. Okay, the next topic is called rationalization. So a number such as 4 divided by 1 plus square root of 3, or 34 divided by square root of 3 need to be rationalized, meaning the bottom number, the denominator, must be an integer. So for rationalization of a number which has the denominator square root of a, you'll need to multiply the fraction by square root of a divided by square root of a, meaning in the sense this won't really change because this would equate to 1. So multiplying something by 1 does not change the value. So yeah, that's the whole theory behind this. And then for any fraction in the form c by a plus square root of b, you'll need to multiply the fraction by a minus square root of b divided by a minus square root of b. This would also equate to 1. So that's fine. So yeah. So here what we're trying to do is write this in the form a squared minus b squared, because we know that a plus, we'll take x plus y into x minus y is by x squared minus y squared. So we're using the same thing here. That's what we're trying to do. So now let's solve a few examples. So this is our first problem. So this would be 5 divided by 3 minus square root of 2. We'd have to multiply this by 3 plus square root of 2 divided by 3 plus square root of 2. So this would be in the form a minus b into a plus b. That would equate to a squared minus b squared. So now what we can do is 5 into 3 plus square root of 2 divided by 3 squared minus square root of 2 squared. Now we can simplify this. We multiply 5 into 3, so that's 15, plus 5 into square root of 2 divided by 3 squared is 9 minus square root of 2 whole squared we just saw is 2. So this would be 15 plus 5 root 2 divided by 7. So we could leave it like this. This is our final answer. So we'd use the same procedure, 2 divided by 3 minus square root of 2 into 3 plus square root of 2 divided by 3 plus square root of 2 equals 6 plus 2 square root of 2 divided by 3 squared is 9, and then this squared would be 2, so that would be 6 plus 2 square root of 2 divided by 7. So that's our answer. You can go ahead and solve these two. I will also solve them now. Okay, so now I'll solve these two problems also. So what we'll have to do is rationalize the denominator. So this would equal square root of 3 plus 2 divided by square root of 3 minus 1. Now we can write this as square root of 3 plus 1 divided by square root of 3 plus 1. So this would be it would be this divided by square root of 3 whole squared plus minus 1 squared. This would equal square root of 3 into square root of 3 is 3 plus square root of 3 plus 2 square root of 3, because this multiplied by this multiplied by this multiplied by this, and this by this, that's 2, divided by square root of 3 whole squared would be 3 minus 1. We could add like terms, so that would be 5 plus 3 square root of 3 divided by 2. Okay, so now let's solve this. Square root of 7 minus 7 divided by square root of 10 plus 4 multiplied by square root of 10 minus 4 divided by square root of 10 minus 4. This would be square root of 10 minus 7 into square root of 10 minus 4 divided by square root of 10 whole squared would be 10 minus 16. This would be 10 minus 4 root 10 minus 7 root 10 plus 28 divided by minus 6. It would be 38 minus 11 root 10 divided by minus 6. This is our final answer. So now let's move on to the next topic in this chapter. So here I've written down a few things. So 7 to the power of 4, this is equivalent to 7 into 7 into 7 into 7 into 7. So 7 multiplied by itself 4 times. So that's what this means. And then 3 to the power of 5 is 3 multiplied by itself 5 times. So 3 into 3. 3 multiplied by 3 multiplied by 3 multiplied by 3 multiplied by 3. And then 5 to the power of 3 is 5 multiplied by itself 3 times. That's the meaning of this. And that would be 5 multiplied by 5 and multiplied by 5. And now let's look at this one. So minus 1 to the power of 1 is minus 1. But then minus 1 to the power of 2 is minus 1 into minus 1 equals 1. And then minus 1 whole to the power of 3 would be minus 1 into minus 1 into minus 1. That would be minus 1. And then minus 1 to the power of 4 would be minus 1 into minus 1 into minus 1 into minus 1. That would be 1, because a negative number multiplied by a negative number would be positive, and a negative number multiplied by a negative number would be positive. So a positive into a positive would be a positive number. So this is what we have derived. So we know that these are the concluding things. So a negative base raised to an odd index, this is the index, to the power of would be the index. So a negative base raised to an odd index is negative, and a negative base raised to an even index is positive. So negative minus 1 is a negative number. When it's raised to an even index, it would be positive. I'd also like to clarify one more thing. So negative 1 whole squared is not equivalent to minus 1 whole squared. This is not equivalent. So minus 1 whole squared would be minus 1 into minus 1. That would be 1. Whereas minus 1, this would be minus 1. Let's also take another example. Let's take minus 8 whole squared. This would be negative 8 into negative 8. That would be 64. Whereas a negative of negative 8 squared would be negative of 8 into 8. That would be negative 64. So these two are two different things. So the next part of this chapter is called as index laws. So a to the power of m multiplied by a to the power of n equals a to the power of m plus n. So this explains this. To multiply numbers with the same base, keep the base same and add the powers. So I'll just show you an example. So for example, 5 to the power of 4 multiplied by 5 to the power of 3. We know that this is 5 into 5 into 5 into 5 into 5 multiplied by 5 multiplied by 5. So there is 1, 2, 3, 4, 5, 6, 7. So that would be 5 to the power of 7. This is equivalent to 5 to the power of 4 plus 3, that is 5 to the power of 7. So therefore this is the law. So the next part states that a to the power of m divided by a to the power of n equals a to the power of m minus n. So to divide numbers with the same base, you'll have to keep the base and subtract the powers. It's very similar to the old one, the previous one. And the next one states that a to the power of m to the power of n equals a to the power of m to the into n. Just you'll have to multiply. So when raising a power to a power, keep the base same and multiply the indices. And then in brackets ab to the power of n. So you'll have to distribute the power of n. So it will be a to the power of n into b to the power of n. So the power of a product is the product of the powers. And then a divided by b to the power of n, it's very similar. It would be a to the power of n divided by b to the power of n. So the power of the quotient is the quotient of the power. And then a to the power of 0 equals 1. And a must not be equal to 0. So any non-zero number raised to the power of 0 is 1. And a to the power of minus 1 equals 1 divided by a to the power of n, and 1 divided by a to the power of minus n equals a to the power of n. And a particular case you'll have to remember is a to the power of minus 1 equals 1 by a, and a must not equal 0. Yeah, so this is all. And now let's move on to the next one. And so we use the index laws that we used previously can be applied to this new one, and it can be written as fractions. So the notation a to the power of n, as we already know, is defined as a multiplied by itself n times. So square root of a will be represented by a to the power of 1 by 2, and cube root, this is the symbol for cube root. So cube root of a equals a to the power of 1 by 3. Therefore, n root of a would be a to the power of 1 by n. So this is how we derive it, this one. So it would be, this one would be a to the power of m divided by n. So now let's solve a few of these examples. Okay, let's start with the first one. So we know that 3 is 3 to the power of 1 and square root of 3 is this. And now we already know this rule, so it would be 3 to the power of 1 plus 1 divided by 2. That would be 3 to the power of 1 by 5. I mean, yeah, 1.5, I mean. So that is 3 by 2. This is our final answer. And now let's move on to the next one. 1 divided by cube root of 32. So 32 can be written as 2 to the power of 5. So it would be cube root of 2 to the power of 5. As we know, this can be written as this. And now we can use another law where we know that 1 divided by a to the power of n equals a to the power of negative n. So it would be 2 to the power of negative 5 by 3. Okay, so the next one, it's 1 divided by this one. 27 can be written as 3 to the power of 3, meaning 3 cubed. So this would be, and then it would be 1 divided by 3 to the power of 3 divided by 4. And then this could be written as 3 to the power of negative 3 divided by 4. So that's our answer. And then let's solve these two. Okay, so 16 can be written as 2 to the power of 4. So that would be cube root of 2 to the power of 4. That would be 1 divided by 2 to the power of 4 divided by 3. That would be 2 to the power of negative 4 divided by 3. The next one, this would be very simple. It's 2 to the power of 1 by 5, and then 2 to the power of 1 by minus 1 by 5. So now let's look at algebraic expansion factorization. This is very simple. So we have a times b plus c within brackets. So it would be ab plus ac. Then a plus b times a plus d, meaning ac, ad, bc, bd. So you'll have to find the sum of all those. And then we know this law. It's a plus b times a minus b. That would be a squared minus b squared. And then a plus b whole square would be a squared plus 2ab plus b squared. Then a minus b whole squared would be a squared minus 2ab plus b squared. These are very simple. You can remember them. Okay, so now let's move on to exponential functions. So an exponential equation or a function is an equation in which the variable occurs as the part of the index or exponent. For example, 2 to the power of x. Here, the variable x occurs as the part of the index or exponent. We also call this as exponent. So we can write 2x, 2 to the power of x equals 8, or 5 to the power of 2x equals 6. And these are exponential equations. And the way to solve them is, if the base numbers are the same, we equate the indices. So if a to the power of x equals a to the power of y, then x to the power of, x equals y. So for instance, 3 to the power of x equals 27. We can write 27 as 3 to the power of 3. So therefore 3 to the power of x equals 3 to the power of 3, implies that x equals 3. So now try to solve these. I will write down the answers and I'll solve them in front of you. Okay, so now let's solve the first one. So we know that 27 is 3 to the power of 3. So we can write 3x plus 1 equals 1 by 3 to the power of 3. And then using the rule 1 by a to the power of n equals a to the power of negative n, we can write 3 to the power of x plus 1 equals 3 to the power of negative 3. And since we know that we can equate this because the bases are same, we can write x plus 1 equals negative 3, implies that x equals negative 4. So this is our solution. Now let's move on to the next one. We can write 128 as 2 to the power of 7, and then we can write 4 as 2 to the power of 2 equals 2 to the power of 7. Since we know that a to the power of m to the power of n equals a to the power of m times n, we can write this as 2 into 2 to the power of 2 into x plus 2 equals 2 to the power of 7. We can equate the exponents. We can write this implies 2x plus 4 equals 7, implies 2x equals 3, implies x equals 1 by 5 or 3 by 2, which is the same thing. So yeah, that's the answer for this question. And now let's move on to the next one. Okay, this one, we can write 1 by 3 as 3 to the power of negative 1. So we can write this as x plus 2, and 9 as 3 squared, implies negative 1 into x plus 2 equals 2, implies negative x, negative 2 equals 2, implies negative x equals negative 4, implies x equals 4. So this is our solution. Now let's solve the last one. 9 can be written as 3 squared. So 3 squared, 2, this will be 3 to the power of negative 1, 2x plus 1, and then 2 into 2x. Okay, so the question was find the value of x if possible. So here, as I solved it, there is no solution. So this won't have any solution. Okay, now let's do exponential functions. The previous slide was supposed to be exponential equations, by the way. So exponential functions, an exponential function is in the form of y equals bx, where b is greater than 0 and b is not equal to 0. Over here we have the graph of y equals 2x. This is the graph. And as x becomes large and negative, meaning it's tending towards negative infinity, the graph of y equals 2 to the power of x approaches the x-axis but never touches it, since it cannot be equal to 0. This cannot be equal to 0. So therefore, however large or small the value of x is, you're never going to get, the y value will never be 0. So therefore, we can conclude that y equals 0 is a horizontal asymptote. We've already discussed about asymptotes. It's where the graph approaches but never touches. So since we have already discussed, I'm not going to go too in depth. Okay, so now let's look at some factors. So for the general exponential function y equals a into b to the power of x minus c plus d, where b is greater than 0 and b is not equal to 0, b is not equal to 1 and a is not equal to 0, b controls this value, controls how steeply the graph increases or decreases. The greater the value of b, the greater or the more steep the graph is. So if this was b was 2, it would be less steep than if b was like maybe 5. Yeah, and then C controls the horizontal translation. So horizontal translation is left to right, like this way, and vertical translation is this way. So, and then D controls the vertical translation. And then the equation of the asymptote is y equals d. So it will look as though it approaches, but it will never touch this line, y equals d. Okay, now let's look at these specific examples. So it would look like this if a is greater than 0, meaning it's increasing, it's concave upwards, it's going up, and then b is greater than 1. And then the graph will be increasing. And if a is greater than 0 and b lies between 0 and 1, it will look something like this. And then if a is less than 0 and b is greater than 1, the function will be decreasing. This is decreasing, this is also decreasing. And if a is less than 0 and b lies between 0 and 1, it will be an increasing graph. Yeah, that's pretty much it for this. So now let's look at some of the graphs. So here, like we have mentioned before, the value of b controls how steeply the graph increases or decreases. So here we can see that y equals 5 to the power of x versus y equals 2 to the power of x. So the value of y to the power of x is increasing more steeply than y equals 2 to the power of x. So over here you can see each and every graph. And that's pretty much it for this chapter. And we're done with this chapter.